Lesson number 3, daily summary. In this lesson, we solve word problems that involve linear equations and we graph lines using intercepts. We also learn how to identify dependent and independent variables, as well as how to write an equation for one variable in terms of another. Reminder, do not use your calculator on any problem in the class packets unless the instructions tell you to do so. A model is a mathematical description of a real-world situation. Suppose an individual works X hours at a salary of $15 per hour. So X is the number of hours, and we're making 15 bucks an hour. Fill in the table of values showing the wages W in dollars earned for the number of hours worked X. Okay, let's give this a shot. So in the first row, if you work 0 hours, what are your wages? Well, sadly, $0. What about in the next row? If you work 4 hours, how do you calculate the wages? Well, we know it's $15 an hour and 4 hours, and hopefully we feel that multiplication is the right thing to do. And so we get $60 for our 4 hours of work. In the next row, if you work 6 hours, that's going to be $15 an hour times 6 hours. That turns out to be 90 bucks. And then finally, 10 hours, 15 times 10, or $150. Plot the points from your table in part A and draw the line that connects those points. Okay, so you're going to have to do some approximating here, I think. So 0, 0 is the first point. But I'll just show you real quick here. You can think of these guys all as being standard looking ordered pairs where X is the input and W is the output. 0, 0 is the origin. I think that's here. It's hard to see on my graph paper. Hopefully it's clearer on yours. 460, so we go over to 4 and then up to 60, which is this one. 690, this one we'll have to estimate, so it's halfway in between the 100 and the 80. And then finally 10, 150. 10 and then 150 is halfway between 140 and 160. And when you're making a straight line, go ahead and use a straight edge, so a ruler or a bookmark or something like that to help. Something like that. Part C, write an equation for W in terms of X. So that phrase is underlined. We're about to define it right here. This means write an equation of the form W equals ... X ... That is my funny way of saying W is by itself on the left-hand side of the equation and X is buried on the right-hand side of the equation, could be surrounded by lots of numbers. It could have lots of X's floating around, like multiple X's, could be powers on the X's, could be anything on the right-hand side with lots of X's. But W in terms of X means specifically that W is by itself in the equation and X is buried on the other side of the equation. So let's see if we can write an equation for W in terms of X. So as soon as I see that phrase, W in terms of, I write W equals. I don't even need to see the X. W in terms of immediately means W equals. And now the X will appear on the right-hand side. How will it appear? Well, if we take a look at the pattern here, that 4 led to 15 times 4. That's 6 led to 15 times 6. And this X is going to lead to 15 times X. That's our formula for the number, for the amount of wages earned when you work X hours. 15 times X. W equals 15 times X. For each increase of 1 hour, how much more does the individual earn? Well, $15. Does this hourly rate change or stay constant? Well, it stays constant. Every hour you make 15 bucks. It doesn't change. Your salary doesn't change. But there are instances where your salary would change. For example, if you work overtime, maybe like the first 40 hours of your work week, you make $15 an hour. But then maybe after that, you make time and a half. And so what would that look like on a graph? Well, let's say for the first 40 hours, you're on this straight line, making 15 bucks an hour. But then if you start to make time and a half, you'll be on a new straight line, a steeper straight line, because you'll be making $22.50 an hour instead of $15 an hour. Okay, but in this case, the rate of change, that $15 per hour, stays constant. For each additional hour worked, there's always an increase of $15. This is an example of a constant rate of change. This constant rate of change between two variables is what distinguishes linear models, this one, from other types of models. Quick detour. Here's the graph of the equation y equals x squared. We will spend some time later this semester graphing equations like this. The graph is called a parabola. Now let's take a look at the rate of change going from point A to B to C to D. First, notice that to go from A to B, we're going 1 unit to the right. And then to go from A to B, we're going 1 unit up. But now let's take a look going from B to C. From B to C, we're going to the right, still 1 unit. But now how much are we going up? Well, we started at 1 and we ended at 4, so I guess we went up 3. And then go from C to D. To the right, we're still going 1. But then up, we're going from 4 to 9. That's up 5. Look at the rates of change. In each case, we went 1 to the right, but then we went up by varying amounts. Up 1, up 3, up 5. Notice that the rate of change is not constant in this graph, since the graph is curvy. The only graphs with a constant rate of change are straight lines, and we're going to be spending a bunch of the first part of this course talking about straight lines. Since our wages depend on the number of hours we work, we call W the dependent variable and X the independent variable. Say it again, the wages depended on the number of hours worked, not the other way. Number of hours worked didn't depend on the number of wages, right? You don't go to your boss and say, hey, I want to earn $300 this week. Here's how many hours I'm going to work. It's here's how many hours I'm going to work. And as a result, after you have worked those hours, you get wages. Your wages depend on the number of hours you worked, not the other way around. In some cases, it's clear what the order is in terms of which variable depends on the other, but in other cases it isn't. The good news is if you have an equation in front of you, like W equals 15x or R equals T over 121, you can know right away which one is the dependent variable and which one is the independent variable, even if you don't know what the letters stand for. There's an easy way to know. So first of all, we said that in the equation W equals 15x, the letter, this W right here is the dependent variable. And it turns out that the dependent variable is always the letter that's by itself in the equation. Say again, the dependent variable is always by itself in the equation, and by process of elimination, the other variable must be the independent variable. So here's a little cutesy mnemonic I came up with. Maybe it will help you remember that the dependent variable is by itself in the equation. So here we go. If it helps, think of Johnny Depp on an island by himself in the movie Pirates of the Caribbean. Thus the dependent, that's almost like dependent variable is the one by itself in the equation, just like Johnny Depp was by himself on an island. So the dependent variable is the one by itself in the equation. Okay, so then in question 2 of the two equations, R equals T over 121 and T equals 121R, write down the one that expresses T in terms of R. T in terms of R. So remember, T in terms of, I don't even need to see the other letter, immediately tells me T equals. So I guess that means that T equals 121R is the equation that expresses T in terms of R. This other equation expresses R in terms of T, which is all well and good, but not what we're after here. Now let's figure out in the equation that we just wrote over there in orange, which variable is dependent and which variable is independent. So remember, the letter that is by itself, like Johnny Depp on an island by himself, is the dependent variable, the dependent variable. So which of these two letters, T or R, is dependent? It's the T, it's the one by itself. Since T is by itself on the island in the equation we just wrote, T is the dependent variable, and therefore by process of elimination, R is the independent variable. So lots of vocabulary. It will become second nature if you use the vocabulary in practice. Okay, last thing for this demo, let's fill in the table with the intercepts of the equation 3x plus 2y equals 12, and then we'll graph the line 3x plus 2y equals 12. So let's take a look at this table here. We've got an x and we've got a y, and we've got ordered pairs x, y in parentheses. And you'll notice that I've picked x equals 0 and then separately y equals 0. So let's talk about this. So let's just plug in the zeros we pick because they're easy to plug in. So let's plug in the 0 for x first. This equation becomes 3 times something plus 2y equals 12. And according to the first row, the something, the x, is 0. So we just put it right there. So 3 times 0 is 0, plus 2y equals 12. 0 doesn't contribute anything there, so that's really 2y equals 12, and divide by 2 to get y equals 6. So we can put right there, y equals 6. And then let's do the second row, same idea, but now we're going to let the y equal 0. So we're going to take this equation and we're going to change it, copy it, but make the one small change, put a blank right there where the y used to be, and in that second row, the y is 0. So 3x plus 2 times 0, that's 0, equal to 12. 3x equals 12, and then finally x equals 4, which we will put here. So we figured out y was 6 and x was 4. It is tempting to plot a point 4, 6. That point is no good. The points that we're interested in are in these two rows, and there's two separate points. There's a 0 and a 6, and there's a 4 and a 0. There is not a 4 and a 6. So let's plot these 2 points, the real points, 0, 6 here, 4, 0 here. You can see that the sort of hybrid point we plotted up there, 4, 6, it's not that it's irrelevant. I mean, it kind of represents both of the points that are on the x and y axes, but it isn't on the line. The line is connecting the dots here. So go ahead and grab your straight edge and connect the dots. That right there is the graph of the equation 3x plus 2y equals 12. And again, at the point 4, 6, it's not on the graph of that equation. Okay, so let's take a look here. It says this is called the intercept method of graphing a line, what we just did, because we found two things called the intercepts. So if we take a look here at our line, you'll see that the point 0, 6 is on the y-axis, and the place where a graph, like the graph of this diagonal line, where the place where a graph crosses the y-axis is called the y-intercept. The point 0, 6 is the y-intercept. Likewise, this point right here, 4, 0, is called the x-intercept. It's the place where the graph, the diagonal line, crosses the x-axis, touches the x-axis. And so here's our little shortcut. If you wanted to find, so notice that this 0, 6, that's the y-intercept. And you see that x is 0. So if you want to find the y-intercept, you let x equal 0. And if you want to find the x-intercept, you let y equal 0. So just as a nice little way to remember that, to find an intercept, you let the other variable equal 0. To find x-intercept, you let y equal 0, not x, the other one, the y. To find a y-intercept, you let x equal 0, the other one. And I think personally, using the intercept method is the simplest way to graph lines of that form. We are going to be talking about mx plus b soon enough in this class. I suspect many of you have seen that before. Some of you feel an obligation that for every for every equation that looks like this, you got to put it in y equals mx plus b form if you want to graph it. And that is not true. Mx plus b form is great for some things, but it is not required. If you're just trying to graph the line, it's not required. We graphed this line without putting it into mx plus b form. So sort of get out of that habit if you feel like you might be there right now. But anyway, down here in bold, in general, to find an intercept, let the other variable equal 0.